So these different investigations today deal with non-oxide refractories like silicon carbide and silicon nitride. The first one I have here is a little bit older one. Thermal shock damage in silicon carbide. And actually, one of the authors here is Brott, Dr. Brott. He was actually my PhD advisor when I was in grad school. But they looked at two silicon carbide refractories that had different fracture surface energies. And they were subjected to thermal shock, where they increased the level of shocking. And they monitored the damage by looking at damping capacity, Young's elastic modulus, and then fracture strength. And they correlated the thermal shock resistance to the fracture surface energy. So this is the slide that we've seen before, fracture strength versus delta T. And region 1, region 2, region 3, and region 4. Region 1 is a constant strength region. There's no fracture initiation. And the R parameter applies there. And R was the fracture strength times 1 minus the Poisson's ratio divided by the elastic modulus and the thermal expansion coefficient. And then region 2, there was a decrease in the strength. Crack propagation took place at some critical delta T. And what really applies there is R4 prime. So that's the work of fracture energy times the elastic modulus divided by the fracture strength squared, and 1 minus 2 times Poisson's ratio. R3 prime also applies to this region too. It does not have the work of fracture in it. And I really recommend using R4 prime here, because our R3 prime lacks the fracture energy. And then region 3, constant strength until we reach a point where we have this quasi-static crack propagation, the gradual decrease in strength. Region 3 may actually be missing in a refractory material. It doesn't have to be there. But RST is the fracture surface energy divided by the strength, the thermal expansion squared, Young's modulus, and that's all to the 1/2 power. So they looked at two silicon carbide materials, an RXB, and the other one was an RXC. They have similar densities, similar elastic moduli. RXC is a little bit stronger. This one's about 17,000, let's say, PSI. This one's about 15,000. The first number here is a diamond ground surface. The second number is the silicon carbide ground surface. So there's a surface finish effect, different grinding techniques, but different size flaws on the surface. So the better the surface finish, the higher the strength. And then the fracture surface energy was measured by multiple techniques here. The work of fracture, a double cantilever beam, and a notch beam technique. But you can see these range from 12 to 15,000. These range from about 24 to almost 30,000. So this one, RXC, is twice the fracture surface energy as RXB. So they looked at the loss in strength at different delta T's in different regions. So the initial loss in strength, region 2, this one was 62%. This one was only 22%. And then the rate of strength loss in the regions 3 and 4, minus 13 and that's minus 14. That's PSI per degrees C, and this one's minus 13. So they're quite similar. The strength loss in what they call region 5 at a very high delta T was 88 and then 55. And the modulus change, and this is times 10 to the 6, was minus 15 and minus 4, which was minus 40% or minus 13%. And then the damping change is times 10 to the 4. This was 90, this was 12, this was a 1,500% increase, and this was a 200% increase. So the higher the damping capacity, the more damage. So looking at these numbers, RXC is much better in thermal shock than RXB. So RXB had the lower fracture surface energy. It had a uniform coarse grain size distribution, and RXC had the higher fracture surface energy. It had a bimodal grain size distribution. So the difference in the grain size distributions created a difference in the fracture surface energy. The test methods they used, the mechanical properties, they looked at the dynamic Young's modulus, the damping capacity, the fracture surface energy by the various techniques, the chevron notch, a single edge notch, double cantilever beam. And then they monitored strength by a 4-point bend test. The thermal shock samples were 1/4 inch by 1/4 inch by 2-inch bars. And the quenching temperatures were 400 to 1200 degrees C. And there were 100 degrees C intervals in that temperature range. They quenched into a brine solution at minus 20 degrees C. Each sample had 1 quench cycle. And then they monitored the damage by Young's modulus, the damping capacity, and the 4-point bend strength. So a little bit more on damping capacity. It's a mechanical property of a material that measures its ability to dissipate elastic strain energy during mechanical vibration or wave propagation. So the damping capacity increases with increasing thermal shock damage. So the more microcracks present, the more damage present, the damping capacity goes up. And it's a pretty sensitive way to measure thermal shock damage. So for this first material, RXB, this is the fracture strength after thermal shock versus the delta T. So there was a 62% loss in strength here when they reached the critical delta T, which is a little over 300 degrees C. There's a region 3 here, region 4, and then they showed the region 5 here. So in region 5, there was a 12% retained strength. So there was a 88% loss in strength on this material. This is the change in damping capacity, delta Q, versus, again, the furnace temperature. And you can see that it goes up until it reaches this point here, about 600 degrees C, where the damage becomes constant. So the damping capacity increases with damage and then levels off. Actually, is slightly decreasing at the higher furnace temperatures. This is the other material, RXC. Again, fracture strength after thermal shock versus the furnace temperature. So this one only had a 22% strength loss. There was no region 3. It went right into quasi-static crack growth, which is what you want for better thermal shock resistance. And it retained 45% strength in this last region, region 5. So it only lost 55% of its strength. And then if you look at the damping capacity changes, delta Q versus the furnace temperature. Same trend. It increases to about 600 degrees C and basically levels off. But this y-axis here goes from 0 to 12, whereas this one went from 0 to 100. So there's a much bigger increase in damping capacity in the first material compared to this one. So this is the furnace temperature. This is RXB, this is RXC. So the delta E over E, and then delta Q over Q. So this one is 0.32, and then this delta E over E is 0.11. So this had a elastic modulus drop at least 3 times more than this one. And then the change in Q over Q, this one is 12, this one's only 2.5. So this one is much better in thermal shock resistance, RXC compared to RXB. And this was the one with the bimodal grain size distribution. So they calculated these different R parameters, and I put them on this graph here. So again, flexural strength after thermal shock versus furnace temperature. And this is RXB. So R was calculated at 103 degrees C. And you can see this delta T was about a little more than 300 degrees C, maybe 320. So R was calculated quite a bit lower, about 100 degrees, whereas the critical delta T in this case was about 300. So R equals delta T. And then R4 prime was 26.9 times 10 to the minus 3 centimeters. And then R3 prime was 2.2 times 10 to the minus 6 squared centimeters per dyne. And then RST in region 3 and 4, 18.8 square root of centimeters degrees C. And I have the same thing here for RXC, fracture strength after thermal shock versus furnace temperature. So this R parameter came out to 137 degrees C. Maybe that's about 350 where we first started to see a drop in the strength. So this one was 103 and this one was 137. So RXC is a little bit higher, but neither one correctly predicted where the first delta T critical is. Again, these may not really apply to refractory material like this. These aren't terribly high strength materials. And in region 2 here, R4 prime was 43.4 times 10 to the minus 3. And back on this other material, RXB, it was 26.9 times 10 to the minus 3. So there's a doubling almost of the R4 prime parameter in region 2, which correctly predicts the trend where this was a substantial strength loss and this was a much lower strength loss. R3 prime here is 1.6 times 10 to the minus 6. Over here, it's 2.2 times 10 to the minus 6. This doesn't really work here, R3 prime. And it doesn't include the work of fracture, so it's not going to predict the right trend in this material because there's a substantial difference in the fracture surface energies. And you can only use R3 prime when there's not a big difference in fracture surface energies. Our RST here is 31.7. It's 18.8 here. So it predicts the right trend. this RST value is much higher for this material RXC with the bimodal grain size distribution. So both R4 prime and RST really work for this material, predicts the difference in the damage. So they summarize this, the microstructure, they're saying the bimodal grain size distribution exhibited increased fracture surface energy compared to the more uniform coarse grain size distribution. So the silicon carbide with the higher fracture surface energy exhibited better thermal shock resistance. So when you have materials that are similar in chemistry and have similar elastic properties, similar thermal expansion behavior, just measuring the work of fracture will rank the materials in general. Young's elastic modulus decreased and the damping capacity increased as the thermal shock damage increased. And comparing Young's modulus to the damping capacity, the damping capacity was more sensitive to thermal shock damage. And the strength changes, the strength losses as a function of the quenching temperature followed trends predicted by both R4 prime and RST. And these materials exhibited similar behavior for the oxide materials we've been looking at. This is a 2002 investigation. I put this one in because this is a very porous material. So this is thermal shock behavior of a porous silicon carbide ceramic. This might be a porous filter for molten metal. So it's a high temperature porous refractory. So they looked at the thermal shock of a porous silicon carbide ceramic, and it was evaluated as a function of the quenching temperature, the number of quenching cycles, and the sample size. So they have a sample size effect here by varying the sample thickness. And they looked at the damage by monitoring the fracture strength. So these are manufactured in a very interesting way. It's oxidation bonding. So you start out with this mixture of powders. This one had about 56% silicon carbide, 18% alumina, and 25% carbon. So these were pressed into shapes, and then they were sintered at 1450 degrees C in air. Sintering this in air burns off the carbon, leaves the pores. The silicon carbide, at least on the surfaces, starts to oxidize to form SiO2, and the SiO2 reacts with the alumina to form some mullite. So this is what the microstructure of this refractory looks like. You have these spherical areas. That's the silicon carbide particles that are now covered with oxide, and they're connected by these oxide necks. So you have these well-developed oxide necks connecting these silicon carbide particles. So this is primarily silicon carbide and alumina, but some of the silicon carbide that oxidize to SiO2 is in the cristobalite form of silica, and some of the silica react with alumina to form mullite. So the mechanical properties, they use a 3-point bend strength method, and the thermal shock bars were 4 by 40 millimeters in cross section, and the thickness was varied from 1.5 to 7.5 millimeters. And they quenched between 200 and 1200 degrees C. And they did a water quench at 20 degrees C water bath. And they ran 1 to 4 cycles on these samples and used the 3-point bend strength to evaluate the damage. So even though they're porous, the pores are pretty small, 3 microns. So that did not allow water to penetrate very quickly into the porous material. So the stresses that developed were still surface tensile stresses because the bulk temperature gradient during quenching didn't change because the water really didn't penetrate the pores in a very short time. So even though it was porous, it was still a severe thermal shock with severe tensile stresses developing. So flexural strength versus temperature difference. These were the 3 millimeter thick samples. You had a point here about 200 degrees C where the strength started to fall off. I would say this kind of fell off pretty rapidly here, but they're in this investigation calling it more gradual. So the kind of damage taking place was these neck regions were cracking. So you can see a neck region here that has a crack in it. Here's another crack. So the weaker neck regions on the surface cracked during the quenching, and the number of cracked necks increased with increasing quenching temperature. So these type of cracks along the neck regions, the density of the cracks increased with increasing temperature. And they noted there was no macroscopic crack propagation. So these cracks were arrested by the pores. So they were only across the neck regions. They didn't continue and form large macroscopic cracks. They were limited to the neck regions as these pores arrested the crack growth. So the number of cracked necks increased with increasing quenching temperature, and that decreases the load-bearing area and it decreases the strength. So that's basically what's happening here. The neck regions are cracking, and at some point, the damage tends to level off. And they observed that the damage basically occurred during the first quenching cycle. So flexural strength versus the number of quenching cycles from 0 to 4. And this was for a quench temperature of 1,000 degrees C on a 3 millimeter thick sample. So here's your initial strength, and then your quenching after 1, 2, 3, and 4 cycles. And the strength didn't change because the amount of damage that occurred all basically took place in the first cycle. Strength also decreased with increasing thickness because the thicker the sample, the larger the thermal stress is. So the thermal stress increased with sample thickness. So again, flexural strength versus thickness, going from about 1.5 to 7.5 millimeters. Unquenched, there was no effect sample size on the flexural strength, but as you increase the sample size, the retained, well, the flexural strength fell off. So this was at 1,000 degrees C, and strength as a function of sample thickness. So the thicker the sample, the higher the stress levels, the bigger the thermal gradient. So in these porous materials, the damage occurred as cracks in the neck regions. These cracks were arrested at the pore, so there was no macroscopic crack propagation. The residual strength of the quench samples gradually decreased with increasing quenching temperature and also sample thickness. And that was due to the cumulative increase of cracks in the neck regions. And the fracture strength of the quench samples was not affected by the number of quench cycles. So the damage basically took place in the first cycle. So I put that one in because it's a very porous material. So you can see how that kind of material behaved. They did not do any R parameter calculations. This one is a silicon nitride material, and they're basically evaluating the strength of silicon nitride after thermal shock. This was done in 2003. So the thermal shock of silicon nitride materials was evaluated as a function of quenching temperature. And they also looked at surface oxidation. So that can affect the thermal shock behavior because the surface oxidation can actually increase the strength by healing surface cracks. So when you oxidize Si3 and 4, you're going to form a silica SiO2 layer, and that viscous layer can heal cracks. It can also generate compressive stresses on the surface. So thermal stresses, which would be opposite effect of surface oxidation, thermal stresses will decrease the strength by forming cracks. But if you have an oxidation process taking place, that could possibly heal the cracks and also put a compressive stress on the surface, which would be the opposite effect of the damage from thermal shock. So damage was monitored by changes in the strength of these materials. So the material was at 95% silicon nitride, Si3 and 4, and then the sintering aid was 5 weight percent YB203. These were hot pressed at a high temperature, 1800 degrees C, under a nitrogen atmosphere to prevent oxidation of the silicon nitride. So 3-point bending was used to measure the mechanical properties. 3 by 4 by 36 millimeter bars was a sample size. And the quenching temperatures were between 600 and 1200 degrees C. These were quenched in water at 20 degrees C at room temperature. Only one cycle for each sample, and then the damage again was monitored by 3-point bend strength on the 3 by 4 by 36 millimeter bars. So they had 3 conditions here, 3 different arrangements for the thermal shock. AE is air exposed on the tensile face. So the tensile face was 36 by 4 millimeters. So here is a sample labeled S. It's 36 millimeters long, 4 millimeters wide. This is the tensile surface. It was encased in a mullite box, basically, that was in 2 pieces, so that when this was dropped into the water bath, this would fall apart and you thermally shock the sample. But AEU was an air-exposed tensile face. So this surface and the thermal shock cycle was exposed to air and subjected to oxidation. Then AU was air unexposed tensile face, so that they also covered this face with an additional mullite plate to prevent oxidation. So AE was allowed to oxidize, AU was not allowed to oxidize. Then AE2 was also exposed, had an air exposed tensile face and under this type of condition, but it was not thermally shocked. So when it went into the furnace for whatever time it was held to equilibrate, instead of dropping it in water, it was allowed to cool very slowly. So it wasn't thermally shocked. So AE was allowed to oxidize during thermal shocking. AU was not allowed to oxidize during thermal shocking. And then AE2 was allowed to oxidize, but was not shocked. So they measured flexural strength versus the quenching temperature. AU was the material that was not allowed to oxidize, so it was covered. So around 600 degrees C, it started to lose strength. So AU, air unexposed tensile phase, gradual loss in strength above 600 degrees C. So no oxidation here and a gradual strength loss due to thermal shock damage. So in this sample that was unexposed to air during a tensile phase, it had a gradual loss in strength. And this is the microstructure of that material. There's some long silicon nitride crystals, elongated crystals. And this is the crack moving in this direction here. The arrows here, they may be hard to see, but you can see two elongated silicon nitride crystals bridging the crack. Here's a third one, partially bridging the crack. It looks like it eventually fractured away from the crack. And here's another one bridging the crack. It looks like it eventually fractured. So we have these crystals bridging the crack in the crack wake, and that gives it this quasi-static crack propagation. It's just a gradual loss in strength with increasing delta T. And we have a more tortuous fracture path, but it also has bridging in the crack wake due to these elongated crystals. AE was the air exposed tensile phase, and you can see it starts to oxidize about somewhere above 600 degrees C, somewhere before 800 degrees C. But now you have a silica layer on the surface of this material, and it increases the strength, and it eventually starts to fall off when the delta T becomes quite large and the stresses build up. But it shows a strength increase of 16% here, 29% here at 800 and 1,000 degrees C, those delta Ts. So this is quite different behavior than we normally see. Here we thermally shock it and the material gets stronger because of the oxidation and the crack healing. And then AE2, which was air exposed on the tensile face, but it was not thermally shocked. It basically shows the same type of behavior as the sample that was thermally shocked AE. It is a little stronger over at the highest delta T for the AE sample. So it is also an oxidized surface. So thermal shocking sample AE had very little effect on its strength. Basically the same as AE2, and there's a little bit of difference as we go to a much higher delta T. So they looked at the fracture surfaces here. The top here is hard to see, it's white, but that's the actual surface of the sample. So this micron marker is 2 microns. So there's a dotted line here. That's about 2 microns below the surface. So surface oxidation causes this crack healing. It can also put compressive stresses on the surface. Anytime you put a compressive surface on a ceramic material, it's going to increase the strength. That's the way tempered glass is made. They put a very high compressive stress on the surface. So when you put it in like a bend bar, you have to overcome that compressive stress before you can start to see a tensile stress. So whether it's oxidation causing crack healing or compressive stress, they both increase the strength. So in sample AE2, which again was air exposed, and this was not thermally shocked. This is at 800 degrees C, and uh, this is not a complete oxidized surface layer. It's partially oxidized. But if you go to the next highest temperature, they use 1,000 degrees C. Again, sample AE2, air exposed, but not shocked. The surface is up here. This is again 2 microns. So it looks like the dotted line is about 3 microns below the surface. So now this white layer up here is your silica glass, let's say, the oxidized layer. It is very dense, it's coherent. So you now have a well-oxidized surface layer. That was where the highest strength increase took place. And then at the highest temperature, again, AE2, air exposed, not thermally shocked, 1,200 degrees C. The surface is up here. It's about 4 microns where this dotted line is. So that's 4 microns below the surface. You still have a dense, coherent, oxidized surface layer. It increased in thickness relative to the sample that was held at 1,000 degrees C. So for this sample, AE, air exposed, pencil, face, um, there was no effect of thermal shock on the strength. So as far as the microstructure is concerned, the surface oxidation caused healing of cracks on the surface and perhaps generated compressive stresses on the surface. The quench sample showed a gradual decrease in strength above 600 degrees C when there was no oxidation. So silicon nitride, unoxidized, showed this quasi-static gradual decrease in strength. The quench samples showed an increase in strength, and we saw a 16% and 29% at 800 and 1,000 degrees C when the sample was exposed to air and allowed to oxidize. So here's an example showing the effect of oxidation on these materials. Silicon nitride and silicon carbide generally will start to oxidize 800 degrees C, but 1,000, 1,200 degrees C, they'll oxidize substantially in air. The silica layer that forms is a diffusional type barrier, and it will slow down the oxidation. And then the other paper I have here, thermal shock resistance and fracture toughness of a liquid phase sintered silicon carbide ceramic. This was a 2009 paper. So they used a liquid phase to sinter the silicon carbide. This was actually primarily silicon carbide. There was some silicon nitride present, so it is basically a composite type material. So they looked at thermal shock and fracture toughness of this silicon carbide, silicon nitride composite type material. It was prepared by liquid phase sintering, and it was evaluated as a function of the heat treatment. They measured fracture toughness by an indentation method, and they used a thermal shock method that's different than any of the ones I've described so far. It's an indentation quench method. So we looked at a single edge notch beam as one technique to measure fracture toughness. That's a very good technique. These indentation methods are not really, have been shown not to be really valid or the best way of measuring fracture toughness, but you can make comparisons on similar material, but it's not going to give you an accurate fracture toughness value. And then in the indentation quench method, indentations were put into the surface before thermal shock. So they were putting in controlled flaw sizes before thermal shocking the material. So in these materials, in situ toughening was noted. So during the heat treatment cycles, um, crystals changed shape. Uh, some became large elongated crystals. And we just saw in the previous material, these elongated crystals were beneficial for thermal shock resistance because they bridged the material in the wake regions. So when you form these elongated crystals in the microstructure, that increases the toughness um, because you're going to activate crack deflection and crack bridging mechanisms. And there's a decrease in strength because the elongated crystals are increasing the flaw size because of the coarser microstructure. So the mixture was one of silicon carbide, silicon nitride, and then the smaller percentages, Al2O3 and Y2O3, they were the sintering aids. These were hot pressed 1850 degrees C in a nitrogen atmosphere. Again, nitrogen was used to prevent oxidation. And these high temperatures and hot pressing produce very dense materials. So there were three compositions they looked at: SN N0 hot pressed, SC N5 hot pressed, and SC N10 hot pressed. So the silicon nitride content, N0 was 0, N5 was 5, and then N10 was 10. So the balance was primarily silicon carbide, and then the smaller percentages of yttrium oxide and aluminum oxide. So hot pressed at 1850 degrees C for 1 hour at 0, 5, and 10 weight percent silicon nitride, the balance primarily being silicon carbide. And then they took some of the same three samples, 0, 5, and 10 weight percent silicon nitride, and they did a post-heat treatment, 1650 degrees C for 5 hours to see if that would change the microstructure and grow the elongated crystals. And they also did the same thing with some of the samples, N0, N5, N10, 0, 5, and 10 weight percent silicon nitride. But this time the post-heat treatment, AN just means annealing, was at a higher temperature, 1850 degrees C for 5 hours. Same temperature as the hot pressing temperature. So the idea here was to grow a in situ type microstructure with elongated crystals. For mechanical properties, they measured hardness by Vickers indentation method. They measured strength in 4-point bending, and they measured fracture toughness by this indentation method. So K1C here is given by this equation, 0.016. E over H. E is the Young's elastic modulus. H is the Vickers hardness. That's to the 1/2 power. And that's times P, which is the indentation load, divided by C to the 3/2 power, which C is the half crack length of the radial crack from the indentation. Again, this isn't bad for comparing K1C for the same type of material. It doesn't necessarily give an accurate K1C value, such as the single edge notch beam. But a lot of work was done with this type of fracture toughness measurement because it's very simple to do. You put an indentation in the sample and you measure the resulting crack lengths. Thermal shock was the indentation quench method, and the crack size they put in, the initial half crack length was about 100 microns. So they used a Vickers indentation to put in a crack, and they used the right loading to give a crack about a 100 micron half crack length. Quenching temperatures range from 100 to 900 degrees C, quenched in water at 20 degrees C. And in this indentation method for measuring thermal shock, you keep shocking the material as, as you're increasing the delta T. So you keep running how many ever cycles it takes with increased delta T until the sample finally fails. So you're just increasing the severity of the quench until that sample actually fails. So this is the sample SCN 10 weight percent silicon nitride, and it was annealed at 1650 degrees C. So this is the Vickers indentation, the diamond indentation that's left in the sample. And you can see the crack pattern, the cracks coming from the corners of the indentation. So these are roughly 100 microns. That was the initial size of the cracks before thermal shocking. This is the same sample, SCN 10 1650 annealing. It was subjected to a delta T of 400 degrees C. And not really a great deal happened. Here, the cracks really didn't extend very much at all. But then the same sample, SCN 10 1650 was the annealing temperature. And now the delta T is 750 degrees C. You can see these cracks grew substantially. So that's basically how the indentation thermal shock test works. You put in cracks of the same size and you keep increasing the delta T until the sample breaks apart. Cracks eventually grow and the sample falls apart. This is the microstructure of the sample SCN0 that's hot pressed. So there's no post annealing, no silicon nitride. So this is a fine grained silicon carbide material, 1 or 2 micron diameter crystals. You can clearly see the grain boundaries and the crystal size. So these were basically fine equiax silicon carbide crystals. This is SCN5 hot pressed, so 5% silicon nitride. Again, primarily silicon carbide crystals, about the same size, 1 or 2 microns, and they're equiaxed. And then the same hot press material, SCN10 with 10% silicon nitride. Again, you see these fine equiax silicon carbide crystals in the 1, maybe 2 micron range. These are the samples that were heat treated at 1850 degrees C. It turns out the samples that were heat treated at 1650 degrees C, either any of these 0, 5, 10 weight percent silicon nitride treated at 1650 degrees C, didn't change the microstructure at all. They looked the same as any of these 3 I just showed. But when they went to the higher temperature annealing cycle, the microstructure changed. Now you have a bimodal grain size distribution. You have these equiax grains, but then you have these long, elongated silicon carbide crystals. So this type of microstructure should be far better in thermal shock resistance. 5% silicon nitride, 1850 degrees C. Again, you have this elongated crystals, and then some of the equiax crystals. And then the one with 10% silicon nitride, again, heat treated 1850 degrees C. You still have the bimodal distribution, elongated and fine silicon carbide crystals. You see some of the finer crystals and then the elongated crystals. So the heat treating at 1850 completely changed the microstructure. So these are the samples. The first three are hot press, 0, 5, and 10% silicon nitride. The second three are hot press, but heat treated at 1650, 0, 5, and 10% silicon nitride. And then the last three are heat treated at 1850 after hot pressing at 0, 5, and 10 weight percent. These are all dense, all about 3.2%, 3.2 grams per cubic centimeter. The percent porosity is almost non-existent. So they're very dense. This is the hardness, the Vickers hardness in gigapascals. They're all about 20, 21. They're all the same hardness. You would expect that. They're all basically silicon carbide. The K1C, by the indentation method, the fracture toughness, megapascal square root of meters, it increases with the elongated microstructure. So it's about almost 3 for the hot press materials, a little higher than 3 for the materials heat treated at 1650. So maybe there was a little bit of coarsening, but the materials heat treated at 1850, it goes up to 4.5, 5.4, maybe 4.4. So there was a increase in fracture toughness. The 4-point bending strength in megapascals. These were maybe 400 to 500, maybe closer to 600 megapascals, maybe 400 to 600 megapascals for the material treated at 1650. These first three were hot pressed, but then the ones treated at 1850, the strength fell off about 142, 391, and 230. So the strength fell off almost half with this 1850 degrees C heat treatment. The fracture toughness not quite double, but it went up. So they calculated R theoretical, and these values are in degrees C, 228 up to 359 for the hot press material, 215 to about 364 for the material with the post heat treatment at 1650 degrees C. But then they fell off 90, 206, 136 for the material that was heat treated at the highest temperature. But then when they measured the thermal shock behavior, the R experimental in degree C really didn't correspond to the theoretical. So these were 300 to maybe 500, 500 to 750. But the materials with the highest toughness and the lowest strength had the highest R values before failure, 650, 815, 760. So this material, the silicon carbide with no silicon nitride, with the post heat treatment at 1650, had intergranular fracture. It looks something like this. You can see the fracture path is going between the grains of silicon carbide. Not a very tortuous fracture path, a small deflection from the main crack. This is not what you want for a thermal shock resistant material. You want to make that crack path as tortuous as possible to increase the fracture surface energy dissipated and make it difficult to fracture the material. This is the same material. This is SCNO N0, SCN0. This is 1650. This is 1850. So this was heat treated at the higher temperature to produce the elongated crystals. And now you can start to see toughening mechanisms being activated. Here's a crack running through the material, but it's bridged by an elongated grain. So there's evidence of crack bridging. This is SCN5 with 5% silicon nitride, but it's, again, at the higher temperature, 1850 degrees C. So you see a crack moving along, it hits an elongated particle, and then it branches, forms two cracks. So crack branching is another toughening mechanism. So in these materials that were cured at 1850 degrees C, you see crack bridging, you see crack branching, these mechanisms being activated. So in this indentation thermal shock test, the results are plotted like this. This is the radial crack length, and this is the delta T. So this is for the hot press samples at 0, 5, and 10% silicon nitride. So the initial crack they put in, and these are half crack lengths, was about 100 microns. So they thermally shocked each sample, and these were an average, I think, of 5. You see the error bars. They thermally shock it, and they measure the crack length on the surface again, and they thermally shock it at a higher temperature, measure the crack length, and then it starts to change. The crack length starts to grow a little bit at about a delta T of 300 degrees C. And then at some point, the crack becomes unstable, it becomes catastrophic, and the sample fractures. So these vertical arrows indicated the delta T's where these materials were no longer in one piece, severe thermal shock damage. This is the material that was heat treated at 1650 degrees C after hot pressing. Again, radial crack length versus delta T, starting out at about 100 microns in crack length. So the cracks are growing substantially. They got up to over 200 microns. And then at some point, looks like delta T's up over 500. There was catastrophic failure. But it was a bit better than for the hot press material by itself. You can see this graph goes to 600. This one goes to 800. So it does a little bit better. And then the material at the post-heat treatment of 1850 degrees C, 0, 5, and 10% silicon nitride, radial crack length versus delta T. And now this is up to 900. So not a lot happening. The cracks are growing slowly, probably in a quasi-static manner. And then at the higher temperatures, over 600 degrees delta T, degrees C delta T, you have unstable crack growth and failure. These are kind of tedious tests to run, but basically the material in this case that had the microstructure with elongated grains had the superior thermal shock resistance because they activated crack bridging, crack deflection type mechanisms. So this was the same table I showed a few minutes ago with density, Vickers hardness, K1C, fracture strength, theoretical R values that were calculated. Then these R's that were taken off the curves, off the plot. So these values are here for these materials. So the materials with the elongated microstructure have the highest delta T's. So when they go from this R parameter that's calculated to an experimental R value, R is for crack initiation, and R4 prime is for crack propagation. So when they change the microstructure from slight annealing here, seemed to increase the toughness a little bit, then annealing at the highest temperature made quite a difference. This R parameter is not really applying. You're starting out with a fine-grained, dense, high-performance technical ceramics, and these aren't that different. These values here, calculated and observed, but you're changing the microstructure from more of a technical ceramic to a higher thermal shock resistant material like a refractory by changing the microstructure. So really, perhaps the R4 prime is more applicable in this case than the R value because it's way off here. So you're going in a transition, I think, from a microstructure, fine grain, high performance to a lower strength, more thermal shock resistant structure. So you're probably making a transition from using an R parameter, and you really probably need an R4 parameter in this case here. So summarizing this, the thermal shock resistance was enhanced with silicon nitride additions to the silicon carbide and with the additional heat treatments, making a coarser microstructure. The heat treatment activated toughening mechanisms, crack deflection, crack branching, crack bridging. And as far as the test methods are concerned, the indentation toughness increased with the elongated type microstructure from 2.88 to 5.39, and that's megapascal square root meters. And then the indentation quench thermal shock resistance increased from a delta T of about 320 degrees C to 850 degrees C. So substantial improvement in thermal shock by changing the microstructure. So that's what I have on non-oxide materials. Next week, we'll spend both lectures on carbon matrix composites. The most common one is an MgO carbon matrix. There's also, we'll look at some other materials like maybe a spinel carbon matrix and an alumina carbon matrix. In all cases, the carbon matrix is there to give a greatly improved thermal shock resistance. So there's a lot more you can do with those materials in varying the carbon contents and the microstructures to really improve the thermal shock resistance. And they made a tremendous difference in a lot of the steel applications in the ladles, electric arc furnaces, and basic oxygen furnace, where these materials have these carbon composite materials have really taken over from all the oxide type materials. So we'll go over those next week. So thanks again for listening in and have a good weekend. I'll see you next Tuesday.